Okay, picking up where we left off yesterday, we were talking about a clinic where 49 out of 207 female patients had live births after getting treated at this reproductive clinic. So the next couple of questions are a little more generic questions about that circumstance. The first one of which is how we can make our margin of error larger or smaller. So we want to know if the clinic wants to cut the stated margin of error in half, how many patients must we use? So we need a different sample size. For a smaller margin, that means we're going to squeeze things in. That means our normal curve has to get skinnier and taller. We're going to need a bigger sample size. How much bigger is the question? So we're kind of going to work backwards because it makes more sense to explain it that way. So I'm going to go ahead and let you in on a secret that the secret is it needs to be 4 times bigger. The question is why. So let's look at the formula for margin of error. The margin of error is what you're adding and subtracting to your p hat. So that's z star times the square root of p hat q hat over n. And I'm going to just say, what if we make n 4 times larger? Just to see what happens. That means we're going to take a new margin of error, ME, and it's going to be z star times the square root of p hat q hat over 4 times n. We're going to increase the sample size by 4 times. Okay, then we have to do a little algebra magic. So there's an understood 1 in front of the p hat q hat, which means there's an understood 1/4 hanging around at the front of this fraction. And I know we're afraid of fractions, but we got to deal with them. And if I take the square root of 1/4, the square root of 1 is 1, square root of 4 is 2. So this actually is 1/2 when you pull it outside the radical. So my new margin of error is z star times 1/2 times square root of p hat q hat over n. And then that half could actually be pulled to the front of that entire set of factors. It just looks prettier that way. So the margin of error is 1/2 times z star times p hat q hat over n. And the z star times p hat q hat over n under the radical is what we started with, so really all we've done is multiply that by 1/2. So we've cut the margin of error in half, did that by making the sample size 4 times larger. The relationship is that if you take the reciprocal of this factor 1/2, that's 2, and square it, you get 4 times larger. Which means if I wanted to be 1/3 as big, I need to make the sample size 3 squared or 9 times larger. And we'll summarize that on a later slide. For now, let's just finish this problem. If the n is 4 times larger, and the original n was 207, the new n would be 4 times 207, which is 828 patients. So we would need to sample 828 patients to get half the margin of error. Bigger sample size means skinnier curve, means smaller margin. Question 2. What might be the potential problem with the sample size above? Well, the only one that really jumps out is that might be kind of big. We have to say less than 10% of our total. And is it reasonable for a reproductive clinic to see more than 8,000 patients in 1998? Well, maybe, maybe not. So 828 may not. We don't know for sure. It's a might. That's the best we can do. Might not be less than 10% of all women seen at the clinic in 1998. So it might be too big a sample. So there's a balance between getting too big and big enough and then getting a margin that's a size that we can work with without going over our sample size. Okay, moving on. More questions about margins of error. We have a new situation, in this case a poll of 1,505, that's our sample size. Likely voters indicated that 52%, that sounds like a p-hat, would vote in favor of a proposed constitutional amendment. A report on the poll said that the margin of error for the poll was 3%. We want to know what level of confidence they used. Okay, so we're working backwards again. Since I know the margin of error, it might be handy to start with the margin of error, which is sort of a formula. Margin of error is Z star times the square root of P hat Q hat over N. If we put in everything that we know, the margin of error is 3%. That's 0.03. Z star is associated with the level of confidence. I don't know that. That's what I'm trying to find. Z star is the Z score. And if I find the Z score, I can find what percentage is under the curve, which would be my level of confidence. So Z star is my go-to piece right now. P hat's 0.52, Q hat's 0.448, sample size is 1,505. And I have to solve that. And that looks daunting, but it's really not at all bad because we need to do 0.03 divided by this package. Because Z star times that whole mess, we just divide by the whole mess and we get Z star. So Z star is 0.03 divided by the mess. Square root of 0.52 times 0.48 over 1,505. And that's calculator work. And you can do division all by yourself on your calculator, so we'll let you crunch that out at your own pace. I'm going to go ahead and tell you what that's equal to. Turns out that's 2.33. So I know a Z-score. This is a Z-score. That is not a level of confidence. A level of confidence is 95%, 90%. What percent of the curve are you hemming in? Which means we're going to have to do a little work with the normal curve. So maybe I'll go over here at the side. Let's sketch out a little picture. If my Z star is 2.33, it means I have 2.33 for my upper Z score and negative 2.33 for my lower Z score. And I'm trying to figure out what percentage of all samples lies in there, because that's going to be my confidence level. So I'm going to need to do normal CDF on my calculator, which I'm going to have some challenge finding. There we go. Whoops. It's a disaster. But you're used to that, so it's not a big deal, right? And we have a light that is not helpful. Let's try that. Alright, this is probably as good as it's going to get today. So we want to do normal CDF, and the lower bound's negative 2.33 and the upper bound's positive 2.33. Those are Z scores, so leave mean and standard deviation 0 and 1, and that's 98%. So 98% of the curve lies between those two Z scores, so my level of confidence is 98%. I'm 98% confident that between 49% and 55% of all voters are going to vote in favor of the proposed constitutional amendment. So we're within 3% of 52. Why might the poll be inconclusive? Well, the interval, let's call it CI, the confidence interval is 3 less than 52%, so that's 49%, to 3 more than 52%, that's 55%. The confidence interval stretches from 49% to 55%, which means if we're as low as 49, it won't pass. If it's as high as 51 or more, it is going to pass because that's a majority. So because the interval includes values below and above 50%, the vote could go either way. All right, we're on the home stretch. 2 done, 2 to go. The next one. During routine screening, a doctor notices that 22% of her adult patients, that sounds like a pea hat, show higher than usual levels of glucose in blood. A group of researchers then decide to conduct a large-scale study, hoping to estimate the proportion to within 4% with 98% confidence. So we have a confidence level, which is associated with a Z-star, and within 4% is code for that's a margin of error. So 0.04 is the margin of error. How many randomly selected adults must they test? We need a formula. We have one. It says margin of error equals Z star times the square root of P hat, Q hat over N. And we'll fill in blanks. Margin of error is 0.04. Z star for 98%, well, we could use inverse normal to find it, but hint, 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 we just saw it on the last slide. It was 2.33. So I'm going to go ahead and cheat and put 2.33 in there since I've already figured it out. And multiply by P hat 0.22 times Q hat 0.78. Why does my telephone keep ringing? Over N, which is, oh, that's what we need to know. Now, we've got a couple choices. We can do some algebra. Divide by 2.33, square both sides, take a reciprocal, and then divide. Or we could use our solver. Lucky for us, we have a CAS calculator, and that would be the practical way to go. So we're going to go to either type the word solve, or we can say menu, algebras 3, and solve. So I'm going to do 0.04 equals 2.33 square root of, and I'm just going to do 0.22 times 0.78 divided by N. I'm not going to worry about the fraction bar. It's going to do left to right anyway. Now you have to go outside the absolute value. Never ends. Okay, so that I said absolute value, it's a square root, and do comma N to tell your calculator to solve for N, and voila, it's going to tell me that that's 582.2-ish. So N equals 582.2-ish. Now that's not a whole number of people. 582 is too small because we need a little more than 582, which means I really need to actually survey 583 people. You have to round up on this one because to go less won't get it done, so you have to round up to the next whole number of people to get a whole person surveyed. 1 to go. I think we can fit it in. Big ideas. The larger the margin of error, well, if you go wider means you have a higher percentage. So the higher, oh, that's not helpful. Look at that. It was off the screen. Let's try again. The larger the margin of error, it means you're reaching out farther than instead of narrower. So farther means a higher percentage, so a higher level of confidence. For a given confidence level, the bigger the sample, the skinnier the graph. So the smaller the margin of error. For a fixed margin of error, so if I'm going to reach out a certain distance, smaller sample means it's going to be shorter and fatter, which means we're actually going to have more confidence because we can have a larger percentage under the curve. Another way you can think about that is for a fixed margin of error, a smaller sample means smaller n, which means a bigger square root, which gives me more confidence. And last but not least, this is summarizing that first slide. For a given confidence level, 95% confident, 90% confident, if we don't change our confidence level, a sample 9 times as large will make a margin of error 1/3 as big. And the general rule is that C times as big That's your n. If your n is c times as big, then your margin of error is 1 over c as big. Now for these kinds of questions, pictures sometimes are helpful, or if all else fails, you could actually pull out the formula and think about what happens if this number gets bigger, if this number gets bigger, and how that all sort of plays in together. And that's over the time limit. It's over 15 minutes. Dang. Shoot. About 30 seconds. I was within 30 seconds.
Rocky, why won't they post over 15?
Because my YouTube is... Actually, that other YouTube channel might let me do more. Of course, it would have been nice if I'd stopped the recording before I danged it. Stop.